We are going to discuss exceptions of VBT theory. If you see 2023 onwards, in all the JE exams or Neet exams, surely they are giving these exceptional VBT questions, and most of the students are doing mistake because everyone know one or two examples of VBT and they think same way even for other complexes and find the wrong answer. So that's why everyone should know these exceptions. So these exceptions surely helps in this. We have covered all the recent JE exam questions and previously which questions came as exceptions. So the first thing, VBT theory explains geometry partially, not even completely, and most of the properties like magnetic behavior, ligand strength, spin state, stability of complex, distortion or Janteller distortion, and back bonding. So most of these properties failed explanation for VBT theory, which means VBT theory doesn't explain these properties. So we'll discuss one by one example. So the first one, these questions are very common in JE exams or Neet exams. CO plus 3 and CO plus 2. So CO plus 3 having higher charge means effective nuclear charge is more. CO2 means less effective nuclear charge, and ionic radius will be more for this because less proton ratio with respect to electrons, but here electron number is less because of high charge. The size will be less, means the proton strongly pull less electrons, and ionic radius, that's what, less for this, more for this. And when the charge means positive charge increase over the metal, the ligand electrons or ligand strongly attract to the metal which have high positive charge. So because of these things, H2O whenever it is with CO plus 3 act as strong field, whenever it is with CO2 plus it act as weak field. Anyhow, the same thing we can discuss with this. Ligand field strength depends not only on the ligand but also the charge and size of the metal ion. So you can see the difference between CO plus 3 and CO plus 2. So this is plus 3, this is plus 2. So oxidation state plus 2 for this, here plus 3. Effective nuclear charge lower for this, higher for this. Because effective nuclear charge increases, size will decrease, ionic radii will decrease. Attraction of ligands. If the metal charge increases, the attraction will be more with ligand because ligand is donor, metal act as Lewis acid in this. So CO plus 3 has higher charge, smaller size, so that very high charge density. These are the reasons why H2O behaves strong field with CO3 plus and weak field with CO2 plus. So coming to the same thing. In case of CO2 plus D7 configuration, in case of CO plus 3 D6 configuration, lower the charge, weaker the attraction for ligand electrons. So higher the charge, strong with ligand electrons. Why it is like that? See, D7 means already electrons present in d orbital, which is 7 electrons, but here 6 electrons are present. Means where more empty orbitals are there comparatively, this have less empty orbitals, CO3 plus have more empty orbitals. When the empty orbitals are more, the ligand electrons easily accept. That's why ligand is more attractive towards the metal which have higher charge. So ligand electron pulled closer, and when the ligand give electrons effectively to the metal, then the CFSE value will be higher. CFSE means crystal field splitting energy. The CFSE happens when ligand approach to the metal or when ligand give electrons to the metal. Why it happens? Because already metal have electrons, ligand also have electrons, between them repulsive forces happens, so that the 5 degenerate or d orbitals going to split 2 levels based on the type of complex in it. Suppose if it is coordination number 6, the T2Z will be lower energy side and EZ will be higher energy side. So the gap between them is CFSE, and the other properties we'll discuss, because we are mainly concentrating on the exceptions of VBT. Means it's not exceptions where VBT theory fail. These are the cases, because VBT theory just give partially about structure or geometry. He didn't consider many properties. The later scientists like CFT or John Teller, these scientists explained why this will happen. That's why these all are the limitations of VBT theory. So large crystal field delta naught is more when the ligand approach to the metal effectively. That means this gap is more, means CFSE is more. You know this even with basic VBT examples, so that we are not concentrating more about that. So delta naught is more means the gap is more. When the gap is more between this T2Z and EZ, so first 3 electrons will go to T2Z. The fourth electron cannot go to EZ if the gap is more, so that pairing happens easily. So this pairing energy is inversely related to pairing. Means if pairing energy is less, pairing takes place. If pairing energy is more, pairing doesn't take place. And CFSE is inversely proportional to pairing energy. So in simple words, pairing takes place if the gap is more. If gap is less, pairing doesn't take place. That's all. So here CFSE or delta naught. Delta naught means CFSE only. It is CFSE for octahedral complex. Or delta O means. So what is the result? Pairing energy is more, which indicates, delta naught is more for this complex CO3 plus, so that pairing takes place. When where pairing generally takes place when the ligand considered as strong field. So what is the conclusion here, students? H2O, if it is with CO3 plus, H2O behaves as strong field ligand. So it's not the nature of H2O changes. H2O is always normal ligand. Depends on the metal charge, the behavior of H2O changing. That's the conclusion point, students. So these are the resultant. No pairing takes place here, and high spin complex H2O behaves as weak field. So instead of knowing this logic, just generally student remember, which is not correct way to analyze. Okay, hope it is clear. The first example, which is exception, same reason, ligand do not change their nature. H2O is always same ligand. So metal ion charge matters, metal ligand interactions matter, and delta naught matters. So H2O act as strong field with CO3 plus, H2O act as weak field with CO2 plus. Hope that is clear. Coming to the next example, students. So next example is most important. Strong field ligand but still high spin complex. Generally strong field ligand, if it is present, the complex is low spin complex, and generally inner orbital complex, general order. But even this also changes in some cases. So that's what this example. Strong field ligand is with metal, still the complex comes under high spin. High spin means more unpaired electrons. Where more unpaired electrons are possible? Where the pairing doesn't take place. This pairing doesn't take place with weak field, but they are telling even with strong field ligand high spin is possible. How it is we can discuss. Rare, but it is important. This is most important example. MnCN6, many times they question asked. Even in Neet exam it was asked. And Mn plus 2, the atomic number is 25. Normal configuration is argon 4s2 3d5, but here 2 electrons removed. First we need to remove from 4s. The resultant is 4s0 3d5. So in this, Cn is strong field ligand. So the order, this we can decide based on the CFSE values or spectrochemical series. So Cn minus is considered as strong field ligand. Even further, there is a simple logic. From left to right, the strength of the ligand decreases. Anyhow, Cn is strong field ligand. So what happens here? These 5 electrons started pairing against Hund's rule because of nature of Cn. That is the general way of understanding, but here that won't occur. The reason for this is D5 configuration still is strong field ligand. So still it comes under as high spin only. That means the pairing is not going to take place. So how the 5 electrons in the normal degenerate state as like this after splitting. So coordination number 6. So T2Z will be down and EZ will be up. So 1 1 1 electron will be, and since Cn is strong field, we generally fill electrons as like this, which is wrong. So the 2 electrons need to fill like this. The reason behind that, even strong field ligand cannot force pairing. The reason for this is this one. For D5 system, pairing is difficult even with strong field ligands. The reason is D5 is highly stable configuration according to symmetry or exchange energies. Symmetry or exchange energies. So that the Mn is stable with D5 instead of pairing. So just based on the stability, it will happen like this. Hope that is clear. So this is most important example. Questions were asked many times in exam. In pyqs only. No color, even it has unpaired electrons. So that is also possible. Generally unpaired electrons means we assume it is having color. But in such cases like Zn plus 2 or Cd plus 2, last 2b group elements. So zinc, cadmium, mercury, if you see, those are having D10 configuration and no color will be existed. Generally student doubt is when unpaired electrons are there, give color, but that's not correct for these cases because color is happening due to DD transition, students. What is meaning of DD transition? The electrons are moving from one d orbital to other d orbital after splitting. So if electron is here, so electron will go here. So like that DD transition, this T2Z d orbital shift to EZ d orbital when light passed over this. So and after that the EZ electron will come back to T2Z or original place by emitting radiation. Based on that radiation, we can decide color of the complex. So what is the conclusion? In these cases, D10 cases, color doesn't happens because no DD transition occurs. So no transition is possible. This asked many times in JEE exam. Hope it is clear. Coming to next, more important example, FeH2O6 plus 2 and COH2O6 plus 3. So here metal having same configuration, means with respect to oxidation state. Fe atomic number 26. So here oxidation state is plus 2, 4s0, 3d6, and CO will be plus 3 here, same 27 atomic number. So 4s0, 3d6. So logically the configurations are same. That doesn't mean properties, everything remains same. So here H2O same, indirectly give the same first example only. D6 high spin and low spin, students. Here metal charge you see. In case of Fe plus 2 charge, in case of CO it is plus 3 charge. So whenever it is plus 2, the effective nuclear charge is less as comparatively CO. If effective nuclear charge is less, the ligand approach will be less. So that's why CO plus 3 has higher charge density, so causes large delta naught, means the gap or CFSE, and delta naught if it is greater, pairing energy is lesser, so pairing happens. So pairing energy is inversely related to pairing, students. Don't get confusion. I will keep this as same clear pattern for the next example. So this is next example where same configuration, different magnetic property. This is most important, and even in 2025 the first paper was having 3 questions related to these examples. The first one is NiCN taken 4 times, NiCl4 2 minus, and this is 2 minus, and one more example is there, NiCO4, students. So this also different property. So why it is like this? I have given, I already uploaded one short video based on this. That's very important and very easy. to follow. So what exactly it is, once again I teach in this. Just if you know, you can skip this, no need to worry. And you can comment also that when you wrote exam, the exam, in which date, and how you wrote also you can comment. How was chemistry paper also you can comment. So here NiCN4 atomic number will be 4s0, 3d, nickel is 8, 3d 8, and 4p also 0, 4d also 0. But in the second case, that means it is 1, 2, 3, you can see this is 1, and second case Ni 2 plus here also. So 4s0, 3d 8, and same way this one. And coming to next one, Ni is 0 oxidation state, 4s0, 3d 8 for the last example students, which is this one, because CO is neutral ligand. Cn is strong field ligand. What happens is, so the electrons, out of 10 electrons of 3d, how many electrons are filled? 8 electrons. So that one empty d orbital you can find. So the electrons started filling from that orbital, from here, because 4 ligands are there. So this 3d 1 orbital filled with ligand electrons, because these are filled with metal electrons, and along with this 4s along with this 4d. So sorry, 4p, here also 2, in p orbital also 2 are filled as like this. So one d orbital, one s orbital, one p orbital, 2 p orbitals are involved. So dsp2 and square planar shape and diamagnetic in nature. So that's what you have to know here. Diamagnetic, square planar, dsp2 is with cn4. Coming to NiCl4. NiCl4, if you take, Cl is weak field ligand, so the d electrons will not pair up against Hund's rule. So electrons will be like this, as like this, 8 electrons. So since the pairing doesn't happens against Hund's rule, so the ligand, that Cl electrons started filling from 4s and 4p. So 4s2, 4p 3. So together how many electrons are there? 6 electrons are there. So that, sorry, 8 electrons are there. It will be with 4s, 1 s orbital, 3 p orbital, sp3 hybridization and tetrahedral shape. Hope it is clear. And does it have any unpaired electrons? No. That is, sorry, there is unpaired electrons, right? Here unpaired electrons are there, so that n value will be 2. So mu equals to under root n into n plus 2 Bohr magnetons. So what you can write, approximately 2.8. For that also I have given one logic point. So it's like a shortcut. N plus 0.8, you can take it as magnetic character, students. Coming to NiCO4. NiCO4 is little different. We generally think CO is strong field ligand, so that dsp2 hybridization, which is wrong. So in case of Ni, slightly different way the pairing happens. So total how many electrons? 8 electrons are there. So as like this. But CO is strong field, so this electron also will be here. Then ligand electrons started filling from this one. This is 3d8. Now it become 3d10 and 4s2 and 4p2. So 4p4, right? Because it started from this dsp2. But here what is the important point? Ligand electrons are filled as like this until here. So the hybridization is dsp2. dsp2 means what is the shape? Square, planar, and diamagnetic. This is most important. Diamagnetic. Okay. So because there will be no unpaired electron. Abnormally, sorry, here, sorry, it will happen like this. Sorry, this one slightly different one, I forgot to write that. So here 3d8 and 4s2 are there, right? 4s2 and 4p0. This is what the actual configuration. So in this case, already since the oxidation state of nickel is 0, this pair of electron will shift here. Then what is the result? 4s will be 0 and 4p also 0. So the electrons started filling from 4s. So it's 1, 2, 3, 4. So what is the hybridization? 1s orbital, 3p orbitals together, sp3 hybridization. So is there any pairing unpaired electrons? No, there will be no unpaired electrons. That's why the conclusion is the paramagnetic complex is only NiCl4. This is diamagnetic, this also diamagnetic, and this will be this alone dsp2, These two are sp3 tetrahedral shape and first one is square planar shape. So these are the overall students what is the important point. And coming to different case, this is also one more different example. Here weak field ligand supports for pairing. Generally weak field ligand is high spin complex or doesn't pair up, but in this case it will pair up. Same reason you can also see one more example. PT is directly proportional to PTCl4 is also having sp3d d to sp3 dsp2 hybridization with a square planar shape. Even Cl is weak field ligand. So the delta naught depends on many factors. Delta naught directly proportional to, CFS directly proportional to oxidation state of metal, directly proportional to 1 by pairing energy, directly proportional to chelation effect, means more the ligands more the delta naught, directly proportional to number of coordinate covalent bonds, and directly proportional to empty d orbitals, and directly proportional to synergic effect or synergic bonding, and directly proportional to strength of the ligand. So higher the strength, support for CFSC. So these are the conclusions about this one. So you can see example COF6, F minus is weak field ligand, still it shows pairing than expected. Why this looks like exception? Students generally think that F minus is weak field ligand, so support for high spin, which is wrong. The reality is CO plus 3 have very high oxidation state. Metal effect partially overcome weak field effect. So the important thing is higher the oxidation state of metal, more the CFSC value, even with weak field ligand. Means high spin is not possible even with weak field ligand when the charge of metal is higher. Okay students, so this is what overall exceptions. Even you can try yourself. There is a question for you. So Cu NH3 taken for plus 2, why it is dsp2 hybridization? You can try. This is one more exception. You try and comment here, or if you don't know, just message me that you can comment that, I will explain. Okay, thank you. Please share and like and subscribe. If you have any doubt, anything, you can comment it, I will surely reply. Thank you students.